So, all of us has come here with the knowledge that there is something between pores going on. And they give us a lot of theory, a lot of experiment, but so far I didn't have the possibility to do by myself. So when I saw the Milifluidics, I decided to attend the workshop. But you end up essentially like this. And then it's even worse because there is a lot of noisy when you're doing the experiment. But at least they are useful, and Filippo especially decided that to contribute really well during this night, going back to the math and check if lamella was there and stuff like that. And this is what we found out.
Yeah, so the first experiment we did was... the first experiment we did was on a conservative tracer. And for this experiment, we wanted to investigate the effect of Peclet number. And the way we did that was by varying the injection rate. So high injection rate, high Peclet number. It might be a little bit hard to see, but with the high Peclet number, we'd expect advection to dominate. So we can see the front is like a little bit more distinct. If we maybe look towards the end, and then lower Peclet number, the front's been diffused, I guess. Hold up, reverse. So apart from the experimental, we wanted to extract some more quantitative metrics, and to do that, we had to do some post-processing. And the first, I guess, gateway post-processing process we did was to look at the mean transverse concentration and the concentration gradient. Maybe the thing to try and pick out in the concentration gradient is this pulse. But it's quite hard because the data is quite noisy. But some more interesting metrics coming your way.
So after a bit of, after a bit of treatment, this is how the evolution of the concentrations look like. And more or less, we could try to fit them to an error function that evolves in time. And so in this way, we could more or less estimate how the dispersion of the solute evolved. So yeah, if we assume that it's an error function, then of course we can say that the derivative over space is equivalent to a pulse injection experiment, and it shows a Gaussian evolution of the plume. If we look at the evolution of the second moment, of the center second moment over time, it shows a slope 2 in the log-log plot. That is what would be a ballistic regime. Normally we should abandon this regime before, like after going through some pores. The thing is that since the whole velocity distribution is not really uniform over the vertical direction, it's not really a uniform injection, then we keep having this ballistic regime. We suppose that if the tank was much bigger, then we would evolve towards something like Fickian dispersion, but we didn't really reach it.
As a second experiment, we wanted to compare the pore scale and the Darcy scale. So we performed two different experiments which had different experimental setup. So on the left, it's the same as before. So you have a high resolution of the image. And on the right, we unfocused the camera to observe a more blurred plume to mimic the Darcy scale. And what did we measure between to compare both experiments? We measure the mixing volume. So if you consider that the tracer concentration is 1 and where you have no tracer is 0, we kept only the volume between 0.1 and 0.9. So that's what we obtained. And here, no, we don't see. Oh shit, we don't see anything. So we also tracked the interface length. So the interface is where the concentration equals 0.5. And normally you should see a lot of finger of this interface, as here it's more like a line, a direct line. And that's that's the results. For the mixing volume, like the experiment for the Darcy scale showed higher mixing volume, but that's probably because of blurring. But what is relevant is the interface length. We can see that it's much higher at the pore scale because of all those fingers and transverse merging. Yeah, so you can't catch this with at the Darcy scale, and that's where mixing appears.
Other really quick point from the Darcy scale experiment is that we had to consider that originally it was saturated with fluorescein, and then we were injecting water. So instead of, as we are computing, usually our signal is getting the fluorescein in the previous pore scale experiment where it was not saturated, and then we injected the fluorescein, we see like the total mass, which is the sum of all the intensity or the signal intensity that we are measuring, is increasing. And in this case, since it had the fluorescein and we were moving the washing the fluorescein out, then it's as if we had a mass, a decrease in mass, but a decrease in the signal.
And then we decided that we wanted to move to something different. And the setup now is vertical, before was planar. And it is saturated with fresh water, the white. And from below, it was saturated with salt water, denser. And we was injecting fresh water, which is now you have an unstable system. So you see that it evolves like this. It's more heterogeneous, the flow field. Still, there are let's say the features of before, but they are completely different because you see here at the real beginning there are some lamella, but then the merging mechanisms are different as before because density is planing. But it was interesting to see it. Then I don't know how to. Oh, somebody knows how to model it properly. Very well done. And then we went to the kitchen for the oil of oil.
Yeah, so Filippo had no car, so he had to go to the kitchen and see the oil flow. We needed to take olive oil. And what you can see here in the left image is like how the water is replaced by oil. And here we had first an oil saturation, which is then afterwards replaced by water. And if we go to the next slide, we can also see like why oil companies have problems in replacing their fluid. So if you look first here at the left scale, we can see like how our oil saturation constantly increases because like the front more or less constantly goes down in this image. Whereas here on the right hand side we see like the imbibition of oil, and we can see that it goes like of water, that goes with like really like fingers, and we can only barely push out the oil, so we already were reaching here a plateau, so therefore we had to increase the flow rate to much higher flow rate so that we could replace the oil with water. And we can see that we have much more fingering in the imbibition case than when we have in the drainage case, and also at the end we still can only replace like 60% of the oil, and 40% of the oil is still like kind of like trapped in the structure, so we cannot take it out with the flow rate. We would have to increase the flow rate even higher to just get more oil out, but it's unfeasible.
We put the fluorescein in the salty water, and then we saturated the medium, and then we injected the fresh water with zero fluorescein.
Thank you, very interesting results. I was wondering if you could measure the contact angle of the olive oil and the
you see that the front is moving for capillary because the flow rate is not that high and just pop throughout the pores.
Do you think it's easier to measure it?
This I don't know.
Well, sure.
Maybe yes.
Is the resolution high enough to like that?
Yeah, the resolution was quite high. So
Maybe if we zoomed in next time,
Yeah.
You wouldn't use that. That's the reason you use it also.
Right. Well, that's really good there. Yeah.
Can you say something about how, maybe I missed it, but I didn't catch how you define and measure the mixing volume? So you showed the length of the interface, but you also talked about the mixing volume on the left?
Yes, I took the threshold concentration is 1, and where you know we don't have a trace 0, so that's water. So I took all the concentration between 0.1 and 0.9.
And you do that,
I did that for
at
both.
the RC and the force
Yeah.
scale?
Josh?
How did you calculate the Peclet number? And given a realistic diffusion coefficient for uranine, do you know anything about where the Peclet number really was?
We didn't. We were playing a lot and we didn't sign.
We did the image, we took the video of it, but images of it, but we actually had a problem getting the mask out of that, so we couldn't ultimately determine exactly.
Do you have any kind of sense of approximately how you might calculate what would be the diffusive time scale for one pore
I
size?
would use the diffusion of fluorescein divided by the mean shear rate between pores.
The other way around.
Or the other way.
But you can also kind of get a sense of the time scale for one pore length, and you could say,
Yeah, well, I mean, between two pores we have diffusion transverse and the shear rate, which is
what do you think about the shape of the displacement front, and how did that come about, and how did that affect your results?
Are you referring to like the interface?
The kind of the arrow shape of it, rather than a flat plane.
Well, that
because it's confined and there is a kind of because it's small, it's confined, and then the mean flow looks like this. It's not a uniform mean flow.
And why is it, and is that due to what effect?
The fact that the Milifluidics is, I mean, it is like this, and maybe you are imposing an higher flow rate, and you create.
we are probably not injecting or extracting uniformly in the inlet and the outlet.
Right, so
But-
it's not an edge effect, I don't think.
No, I think
It's an inlet and outlet effect.
I think so,
Mm,
but I'm not
must
sure.
disagree.
All the solids in there have a zero velocity boundary condition. So all the surfaces are zero.
It's not when we don't have the video, but we did also the stable configuration, injection of different density fluid with two densities for the stable, and there you see that it's really flat, the front.
If it's
which-
density stabilized.
Yes.
Yeah.
Which means that the kind of injection type are the same. But once we advance this front, is stabilizing, it's destroying the parabolic flow field, which to me it makes sense that the parabolic flow field is not due to the type of injection, but is more related with the confinement of the. Because when that is stable density, and the injection mode are the same, but that guy disappears.
That's, I think I would argue with that.
Me too.
You have a question?
Yeah, in the drainage you had something like 90% of recovery. I guess, I'm not sure.
We had like 9%, yeah.
So basically, I think that the real proof media should, the PC length should be much higher, and then the recovery should be like much less. So do you have like any idea if there is like anything else to like make this media more porous and like to rise the capillary?
I don't know. I'm sorry.
Sorry, what was it?
I said if there is like any sort of technology to make this one like more porous.
I can get to reduce the residual.
Should be like to increase the capillary pressure in this system. I guess the capillary pressure is not much, and I guess this fingering is like stimulated by the capillary. So I think like in the real system, maybe this fingering should be much higher than what is observed here.
That was me. You looking like a finger?
No, I mean the real like fingering that I guess is observed in the real pulse media should be much longer than what is observed here in the lab.
For intuition or for drainage?
I mean, in those tests that you showed,
Yeah. There are two things. Not only is it on one side drainage and inhibition, but in addition, in one case it's viscously stabilized, and in the other case it's viscously unstabilized. So it's mostly that the issue.
it's also vertical.
No, it was flat. It was flat.
I think it was a good idea to try for the Darcy scale experiment to blur the camera. And it looks good, but do you think that it's really the same as taking the average concentration? And did you check, for example, that the mass is the same in the Darcy scale experiment as in the post scale? So my question is, when you blur the camera, is it the same as taking the average
No.
over a given scale?
No, it's not. It's definitely not.
If you normalize,
The fingers, so you are blurring all the fingers, so you add the mass.
So you think that you would have more mass in your Darcy scale experiment?
well, you should normalize because actually you are blurring, so you are saying that you have mass over all the space. But if you normalize over the mass, I think it could resemble a Darcy experiment. I don't know.
Can you say a bit more about that? Why do you think that it's not the same as everything?
Sorry?
No, I,
Is it reasonable that it should be the same as everything?
no, I'm saying that you would have to normalize the mass.
Sure.
That's all.
But about the everything part, so I think I saw a bunch of you shake your head when.
Oh, well, I shake my head primarily because I think you're right. If you're blurring it out, you can assume that it's some kind of averaging. But you also have the effect of the image processing. The way in which we did the image processing perhaps didn't capture the full effect of what the Darcy scale was,
So
how the Darcy scale
so
was.
you think maybe you could do it with different calibration or something like this?
I think you could tweak it to make it more representative for sure. Maybe in a bigger setup, it was quite a small system as well, so maybe it wouldn't have been fully representative.
I just want to comment that I think if you want, probably it's more correct to actually do a blurring of the four-scale experiment than compared to the two. So this was kind of an optical trick, but it's optics. So what you have in your image goes through the process that is not necessarily linear. So
So you think you could justify it with frontal path?
yeah, but that was really nice to actually show that by blurring we did something that we can
Yeah.
And
And in some plot we didn't show, but we had normalized how the first moment was varying with time in the area in which there was like the front of the plume. It was more or less, the normalized, it was more or less the same.
But you show it here.
Yeah, no,
So one thing to think about is that the apparent light transmission follows Beer's law. Beer's law is nonlinear. That is to say, if you double the concentration, if you go from 50% illumination to 25% illumination, that would be a doubling of concentration. You only have a quarter change in apparent light intensity. So just like in the lecture about the dawn color numbers and the different pathways, when you're averaging over nonlinear processes, the average doesn't reflect the true mass average. So actually, because of Beer's law, light attenuation, the average concentration would not be correct.
No, so we did not do it here, but like when they are at the university, they test the concentration, like measure different concentration with different light intensities, and like for deconcentration, which we used, we can assume that it's like really linear increase for concentration and also light intensity.
Because it's fluorescing, it's not attenuating.
Yeah.
Otherwise, anyway, we could convert to concentrations first and then blur, right? we could, anyways, we could convert from intensity to concentration and then blur, and it would be,
I stand
or
corrected.